My name is MathYou, and in this section we're going to talk about absolute extrema. Absolute extrema, or extrema, are the absolute maximum or minimum values of a function. And there's a written reminder in here somewhere, which we'll get to, that reminds us that the absolute extrema are referring to y values. It's possible that the largest y value or the smallest y value on a particular function could occur multiple times, and unless we're asked for when those multiple occurrences occur, we're going to answer with a y value. If we're asked when the maximum, absolute maximum, or absolute minimum occur, then we can answer with one x value or possibly multiple x values. Or if we're working with a sine curve or a cosine or something like that, something that is periodic, maybe we'll answer with infinitely many x values, which would be interesting. But we're not going to do that right away. We're going to focus on the types of functions that we've seen thus far and try to find the absolute extrema. So let's sort of cruise through these notes. We'll talk about some concepts. Sophie's going to help us, of course, as she likes to do. And we'll work through some example problems as we go. So a function can have more than one relative maximum or minimum, but we're going to be looking for an absolute max and or minimum. So there is only going to be one each of those. The greatest possible value, y value that is, of a function is called the absolute maximum. The least possible value is called the absolute minimum. And some functions, like a cubic that we're seeing in this graph right here in the middle of your screen, might not have an absolute maximum or minimum, because as that function goes off to the right, it continues getting larger and larger, and as it goes off to the left, it keeps getting lower and lower. Don't jump up there. Please don't jump up there. No, don't do it. She's not even one yet, so she's still exploring. Clearly. Thank you. The only way that this function is going to have an absolute maximum or minimum is if we restrict the domain. So if we were to look at that function on some particular interval, perhaps from -1, 2, 3, 4, maybe from -5. I don't know why my pen's not writing. Oh, the opacity is wrong. If we looked at it from -5 to +1, 2, 3, let's say +3, if we just restricted the domain to those x values, then we would have an absolute maximum of 1, 2, 3, 4, 5, 6. And we would have a relative, well, the minimum is off the screen. But the relative minimum, or sorry, the absolute minimum would be down there somewhere. The absolute minimum would occur when 1, 2, 3, 4, 5, when x equals -5. I can't tell what the absolute minimum is on this particular graph because it goes off the screen on that interval. And the absolute maximum is 1, 2, 3, 4, 5, 6. And that occurs when x equals +3. But again, if I hadn't gone in and restricted the domain, then this function would have, I suppose you could say it's got an absolute maximum of +infinity and an absolute minimum of -infinity. These are, in this sort of sand-colored box, we're seeing more mathematical ways, or a more mathematical way to describe that we're talking about an absolute minimum or maximum. Sophie, I have reached my absolute maximum amount of patience with you. Say goodbye, Sophie. Bye-bye. You're going to go play outside, which means you're going to meow a whole bunch, but we're going to put up with it. Otherwise, we won't get any work done. So an absolute maximum happens if at some particular x value c, f of c, which is a y value, is larger than all the rest of the y values. And it's a minimum if at f of c, or rather if f of c, which is a y value, is less than or equal to all the rest of the y values. For every x in a particular interval. Now we're not always going to be restricting the interval. Sometimes yes, sometimes no. There's that written note that says, remember that these relative extremum and here in this section absolute extremum are talking about y values and not x values. So there is an extreme value theorem, and the extreme value theorem says that a function f that is continuous on a closed interval, I'm in this sand-colored box down here, on a closed interval from a to b will have both an absolute maximum and an absolute minimum. That's good to know. So if we run into an absolute max or absolute min problem, we know that there's going to be an answer. And finally, an example. So we're starting off with a graphical example and not just looking at a function just yet. And what would we say in this example is the absolute maximum and minimum? And what's its location for the function? So the absolute maximum, which is our largest y value, is occurring right here at the top of this hill, so to speak, and it looks like it has a y value of 4. So I would say that our absolute maximum is 4, and our absolute minimum occurs here and here. So the y value of 0, which is the y value of both this point and this point, is less than or equal to the y values of all other points on this graph. So we would say that the maximum, or absolute max, is 4. The absolute minimum is 0. When does the absolute max occur? When x equals 0. When does the absolute minimum happen? It occurs when x equals -3 and when x equals +3. So remember, I'll just say one more time, the answer to the question what, if I'm asking you what is the maximum or minimum, you're answering with a y value. If I ask you when is the max or min occurring, you're going to answer with an x value or x values, right? Plural, x values. How do we find absolute extrema if we're just looking at a function? Here's a step-by-step process that we can use, and you're familiar with all of these steps already. Step number 1, we're going to find the critical numbers, and we know how to do that. Take the first derivative, set it equal to 0. We do need to check and make sure that the x values that are returned to us correspond to points, x comma y, to points that are actually local minimums and maximums. Number 2, we're going to evaluate f for all of the critical numbers. So I just mentioned that. That's part of the process. We need the corresponding y values. We're going to evaluate f at the end points, a and b, on the interval, because it's possible that if we're looking at a function like this, while the first derivative at this point is equal to 0, that's a relative maximum. Our absolute maximum is happening all the way to the right at the end of our interval at the x coordinate, when x equals b. So we need to check what y values are occurring at the leftmost and rightmost point. In other words, the end points of our interval. And step number 4 is just a comparison process. We're going to pick the largest one, y value, and call that the absolute maximum. And we'll find the smallest y value and call it the absolute minimum. So let's see what happens. Find the absolute maximum of this function. All right, so step number 1, let's find some critical numbers. I'm going to take the first derivative, f prime of x is equal to 2x, and then I will set that equal to 0 and solve. And I get 0 equals x. Poorly written, but a true statement nonetheless. 0 equals 0 was true, but 0 equals x. So we do have either a relative max or a min at the point where x equals 0, or when x equals 0. Let's find its corresponding y value right away. F of 0. So I'm taking 0 and plugging it back into my original function now. And f of 0 is equal to 0 squared minus 4, which equals -4. So I'm going to write down this point 0, -4. And I think I'll even put a circle around it to make sure it doesn't wander off. I want it to catch my eye. Let's also, so that was actually step number 1 and step number 2. We evaluated our function for that critical number. Number 3 says evaluate for our endpoints. Now notice we're only working on this little interval that goes from -1 to +2. So let's evaluate. So this was really 1 and 2. And for number 3, let's find f of -1. That is equal to -1 quantity squared minus 4. That's +1 minus 4, which is equal to -3, which corresponds to the point -1, -3. Hold on to that one. And we're going to evaluate the other endpoint, which happens when x equals +2. There's the +2 squared minus 4. 4 minus 4 is 0. So the actual point is 2, 0. And the question asks us to find the absolute maximum. So step number 4 is we need to look at our y values, compare them, and choose the largest one. So which point, which y value is the largest one? It's 0. So 0 is the largest. How does it phrase it in these steps? The largest value is the largest. We'll say y value. Therefore, 0 is the absolute maximum. Zero is the absolute maximum. If the question says also find all values of x where it occurs, the answer to that is 0 is the absolute max when x equals 2. So that's the other part of that answer. Right, so we go through, we find some x values. First of all, by taking the first derivative and setting it equal to 0. Then we pile on with another couple of x values. Those are the x values that are the endpoints of our interval, if we're working with a restricted interval. Then we find all of the corresponding y values for those x values, and we do a little comparison. You can do all of that pretty much in whatever order you want to. You could calculate the y values at the endpoint first if you wanted to, and then take the first derivative and set it equal to 0. Solve and find that y value. But I would recommend, from about 10 years of experience in the classroom, I would recommend trying to keep a consistent process. You're more likely to recall the process if you do it consistently in the same order. Find the absolute minimum this time in this example of the function f of x equals 1 over x plus 2, as well as when that minimum occurs on the interval from -4 to 1. Great. So let's use the same set of steps. Let's find our first derivative. So we have f prime of x is equal to, you could use the quotient rule. If I were me, which I am incidentally, I would rewrite this as equaling x plus 2 to the -1st power. That way I can take my exponent, multiply it out front. There's the -1 times, keep the original inner function, x plus 2, decrease the exponent by 1, which makes it a -2, multiplied by the derivative of the inner function, the chain rule, which just returns a 1 in this case, so that's not very eventful. And then let's rewrite this, clean it up a little bit. We get -1 over x plus 2 squared. And now we're going to take this and we're going to set it equal to 0. 0 equals -1 over x plus 2 quantity squared. The only way you can make a fraction equal to 0 is by making the denominator infinitely large in the positive or negative direction, but we're not working with limits at the moment, or to make the numerator of the fraction equal to 0. Unfortunately, the numerator of this fraction is equal to -1. It's a constant value, so there's no solution to this little equation we're looking at here. All right, no solution. So at least not even on this restricted interval, it appears that for no x value is this function going to have a horizontal tangent line. So there are no relative minimums or maximums. Step number 2, how was it described? Evaluate f for all critical numbers. No solution, therefore no critical numbers. Very good. There's number 2. Number 3 tells us right at the top of the screen to evaluate our function for the endpoints. Let's do that. Number 3, we need f of -4, which is 1 over -4, plus 2, which is equal to 1 over -2, or -1/2 if you wish. So that corresponds to the point, that's an arrow by the way, -4, -1/2. And then let's evaluate at our other endpoint. So that's f of 1, that's equal to 1 over 1 plus 2, that's equal to 1 over 3, which corresponds to the point 1, 1/3. Step number 4 tells us to compare the y values that we found. That's the y value in this point and the y value in this point. We're looking for the absolute minimum. Absolute minimum of -1/2 when x equals -4. And that's your final answer. I wrote it a little bit differently, but we can still put a box around it. First derivative, set it equal to 0. See what you can do. In this case, it didn't pan out. Step number 2, find its corresponding y value. Didn't have to do that because we never found that x value in step number 1. Step number 3 is easy. You're just taking 2 x values and plugging them into your initial function. And number 4 is a comparison process, which I think you can handle. So this is not a very strenuous process, which is great. The critical point theorem, suppose that a function f is continuous on an interval, and that f has exactly one critical number. So there's only one x value that sort of pairs up with the first derivative equaling 0. And they're telling us that on the interval, let's say that that happens when x equals c. If our function has a relative maximum at x equals c, then that relative maximum is also the absolute maximum on the interval. And if there's a relative min, then that relative min is also the absolute minimum. Interesting. Let's have one more look. We have a continuous function on an interval. The function has exactly one critical number. Now, let's just compare this to something we've already worked with. Let's look at problem number 1. This was a continuous function on the interval from -1 to 2. It had exactly one critical number, an x value of 0, which corresponded to a y value of -4, and we were looking for the absolute maximum. Now, if I had asked you for the absolute minimum, that y value of -4 would have been the absolute minimum. And look, if you compare it to the endpoints, neither one of those y values is lower than the y value that we found corresponding to the critical number of x equals 0. So at least for that one example, it appears that the critical point theorem works. And the fact that it's a theorem leads me to believe that I can probably trust it's going to work every time. In example number 3, we're being asked to find the absolute extrema of this particular function, 10 times x times the natural log of x. The absolute extrema is plural, so that's the absolute max and the absolute min is what we're being asked for here. We are to find them if they exist, it says, as well as where they occur, or as I like to say, when they occur. So we're looking for x values and y values of the max and the min. Let's see what we can do. Let's take the first derivative of our function. F prime of x is equal to, I'm going to take the 10 and factor it out of the derivative process so that I'm really only looking at the x times natural log of x. That's a product, so I'm going to use the product rule. I like to keep my first factor and multiply by the derivative of the second. Derivative of natural log of x is 1 over x, plus derivative of the first factor, the derivative of x is 1, times, keep the second factor, that's the natural log of x. So this is equal to 10 plus 10 natural log of x. I distributed the multiplication by 10 and I reduced here. X divided by x doesn't cancel out gone, it cancels out and turns into a 1. And therefore we take the 10 and we distribute it and multiply it by the 1 and we get this 10. And then we take the 10 and we distribute it over here to the natural log of x and we get 10 natural log of x. Alright, so now you know where all of this stuff came from. Great. Let's take that and set it equal to 0. How about 0 equals 10 plus 10 natural log of x? And I'll subtract 10 from both sides. And I'll divide both sides by 10. And now we need to solve for x finally. In order to do that, I'm going to make the left hand and right hand sides of this equation an exponent over e. So I'm going to put another little arrow down here that shows I'm still working on it. I'm going to write this as e to the -1 equals e to the natural log of x. Now e and natural log cancel each other out when they're used this way, or if it were the natural log of e to a power, they would also cancel out there. And we get this as our only critical number. So we're going to have a relative maximum or minimum when x equals e to the -1st power. So I think I'll circle this for the moment, and then I'm going to evaluate right away our original function for the x value e equals -1. F of e to the -1 equals 10 times e to the -1 times the natural log of e to the -1. Now here's that other instance of the natural log and e canceling out, so that's going to leave us just with a -1. And if we simplify, it's not a lot of simplification, just clean it up a little bit. We could write this as -10 times e to the -1st power, or we can write it as -10 over e, whichever you prefer. I think I'll write it over e. So this corresponds to, and now I'm thinking I'm going to go back with the eraser. I'm going to erase this circle that I drawn here and I'm going to save that circle for, let's turn this into an arrow, so that this corresponds to the point e to the negative 1, comma, negative 10 over e. This is one of the points that we're going to be using when we get to the comparison phase in step 4. So we'll be looking at that y value again. All right, let's evaluate our function at the endpoints. There are no endpoints here. We're not being given any kind of a restricted domain at all. So this problem gets a little bit tricky here. We've accomplished steps numbers 1 and 2. And are there any restrictions on our original function sort of inherently? Can I take 10 and multiply it by whatever I want? Yes. Can I then multiply that by the natural log of whatever I want? No. Our x values must be strictly greater than 0. So I'm going to switch colors and come in here and put in a little note that says x must be strictly greater than 0. So how am I supposed to figure out what to do with this point that we found? I have nothing else to compare it to. Maybe it's a relative max, maybe it's a relative min. We're going to make that determination by using the second derivative test. Our other option would be to use the first derivative and check and see if our function is decreasing or increasing to the left of and to the right of the point where our x value equals e to the negative 1, where we have a suspected either maximum or a minimum. So we could do that, but I think in this case, because our first derivative, right at the end of this first line, remember this was, I shouldn't be putting a box around that, let's put a circle around this. This was our first derivative. Finding our second derivative will be very easy, so let's use a second derivative test. Let's find f double prime of x, and that is equal to, now the derivative of 10 is 0 plus, so let's put that, 0 plus 10 times, and then the derivative of the natural log is 1 over x. So our second derivative is equal to 10 over x. And we're going to test the x value of e to the negative 1 in our second derivative to test for concavity. So we need f double prime of e to the negative first power equals 10 over e to the negative first power, which is equivalent to 10 times e to the first power. So I used the fact that our e is being raised to a negative exponent in the denominator. I've made the exponent positive in order to relocate it, so to speak, and push it up into the numerator. Remember that this is the same thing as 1 over e, so I'm really multiplying by the reciprocal. Either way, we end up with e in our numerator, and I've got 10 times e. I don't care what 10 times e is. The only thing I care about is the fact that this is greater than 0. I happen to know that e is approximately 2.8. I believe it's 2.8, or is it 2.7? Let me remind myself. E to the first power is 2.718281828. Those are the first 9 decimal places. It does not repeat after that. Those just happen to be the first 9 decimal places. So 2.7 is a positive number. Times 10, still a positive number. So I know that 10e is greater than 0. Therefore, if I can draw an arrow there, there we go, concave up. Therefore, there's a minimum at the point when x equals e to the negative first power. And we've already calculated our y value. Minimum. And we know that this is the absolute minimum because, is this going to scroll? Here we go. Because of the critical point theorem. We have a function that's continuous on an interval. And in fact, as long as our x values are greater than 0, our function will be continuous for all positive x values. And we had exactly one critical number, which we found by setting our first derivative equal to 0. So that gave us our one critical number, and so we knew that once we determined whether that critical number was locating a minimum or a maximum for us, that was going to be the absolute maximum or minimum. So again, step number 1, find the first derivative. Step number 1b, let's say, is taking that first derivative and setting it equal to 0. I just want to go up and reference, I don't know if you noticed there was a little jump in this video. I had to pause it for a moment, and that moment turned into a long moment. So I just want to make sure that I'm referencing these steps correctly and sort of numbering them correctly. We found the critical numbers, and we did that by setting it equal to 0. Okay, so that was all still part of step number 1. And then step number 2, we found the corresponding y value, so that's labeled correctly. And step number 3, we didn't check any endpoints. And then step number 4, there's not really anything to compare it to. So in this critical value theorem, critical point theorem, the only thing we had to do was determine whether or not it was a maximum or a minimum. And we did that using the second derivative test. So in your notes, it would be a good idea for you to label this part of the process as finding the second derivative. That's what we did here. And then plugging in the x value of our either minimum or maximum, our critical value. We plugged that in order to test for concavity, and then concavity allowed us to draw the conclusion that it was in fact, or is in fact, a minimum. It's not just a relative minimum, but by the critical point theorem, it's an absolute minimum. Let's make sure we answer the question. Find the absolute extrema. There's only one. It's an absolute minimum. What is it? Negative 10 over e. That is the absolute minimum. If it exists, as well as where they occur, well, there's only one of them, so where it occurs is where x equals e to the negative first power, or 1 over e. And the last example is an applied problem. We're looking at maximum profit here, or we're trying to maximize profit, which is a good idea. We're being given a profit function, and this profit function is defined for x values that are greater than or equal to 5. It's an approximation to the total profit, as measured in thousands of dollars. So P of x, the y values, are in thousands of dollars from the sale of x 100,000 tires. So an x value of 5 actually represents 500,000 tires. Find the number of 100,000 tires. So we're not going to have to add 5 zeros to our answer. They're asking us to find the number of 100,000s of tires that must be sold in order to maximize profit. I wanted to mention, because it would be a nice idea to do this here also. In the previous problem, use your graphing calculator or go into desmos.com or whatever other graphing utility you like. And I recommend graphing that previous function that we were looking at, 10x natural log of x, I believe it was, and have a look at where the absolute minimum occurs. The x coordinate is somewhere between 0 and 1. That function is only defined where your x values were greater than 0 anyway, so you can forget about quadrants 2 and 3. And it just dips down into the fourth quadrant a little bit, but go in there and see what it looks like so that you can have sort of a visual to go along with the algebra that we were doing. And I wouldn't hesitate to do that here also. So there's our profit function. Well, we know how to go through these steps. Now also, this is a cubic function. I see it's a third degree polynomial because the largest exponent is 3. And that means, and it has a negative leading coefficient, so that tells us about end behavior. Our function's going to look something like this, or it could look something like this, right? So our hope is that we're going to end up with a maximum value. So let's go through the steps. First things first, we need a first derivative. So let's find p prime, which is our marginal profit function. That's equal to negative 3x squared plus 27, jumped the gun there on the x, 27x minus 60. And then let's set this equal to 0. Did it again. Don't know what my deal is there. Eager to write that x. And now we have to solve this. My recommendation, if you're doing this using paper and pencil, I would divide this entire equation by 3, or negative 3 would be even better. That gives us 0 equals positive x squared minus 9x plus 20. And, excuse me, and is this factorable? 1 times 20, 2 times 10, that's not going to make a negative 9 for us. 3 doesn't work. Ooh, 4 and 5 work. And it's going to be a negative 4 and a negative 5, in fact. So let's factor the right-hand side of this. I was just doing the AC method in my head, basically. X minus 4 times x minus 5. And that gives us an x value of positive 4 would make that statement true, or an x value of positive 5 would make that statement true. So maybe one of those is going to be a relative minimum and one of them is going to be a relative maximum. Let's go ahead, as we've been doing so far, and immediately calculate p of 4 and p of 5 so that we have those y values at the ready. Again, you don't have to calculate those right now, but as long as we're here looking at those x values, let's just do it. P of 4 equals, P of 5 equals. I'm going to pause real quick and I'm going to just drop these two values into a calculator so that you don't have to see me write all this out longhand. No point in doing that. And the next time I see you, two numbers are going to appear next to those equal signs with the corresponding y values for selling 400,000 and 500,000 tires. That's a lot of profit, I hope. All right, so there are our two corresponding y values, and what I did, I'm using a TI-84, and I went into y equals mode, and I typed in this equation. And then, in the top left corner of my calculator, or near the top left, I've got a button that says second, and I hit second, and then where my F4 button is, I know that it's blurry, but where F4 is, above it, it says Calc. And so I hit the second button first, and then I hit Calc, and then I got this menu, which I don't even know why I hold this up. It's like impossible for you to see this. I have to hold it back here so it's even in focus, but I don't even know that helps. But there's a menu system that's on the screen, and the first option is value. And if I hit enter, I get a prompt on my screen under the graph of this function that says x equals, and then I've got a blinking cursor. And I was able to type 4 and hit enter, and it spit out this y value of 12. And then I hit second calc again, and value is the first option in that menu screen that appears. And I hit enter, and I've got my x equals with the blinking cursor, and I typed 5, enter, and it returned to this y value of 12.5. Also, when I very first typed in this equation into y equals mode on this calculator, I hit the graph button, and the standard zoom window on this calculator has positive and negative 10 on the x-axis and positive and negative 10 vertically on the y-axis. And there was no graph to be seen. It churned for a little while like it was trying to graph it, and then I got nothing. So what I did is I hit the, I hit the zoom button and then I scrolled down. I actually knew that this was 0, but option 0 in my zoom menu says zoom fit. And let's see if I tilt this just right. You might be able to read it, especially if you're full screen. So option 0 after I scroll down says zoom fit, and when I hit enter on that option, it spins for a little while and then it starts drawing. There it is. It started drawing my graph. Now a bunch of this, it's only graphed the first 2 quadrants. Quadrants 1 and quadrant 2, top right and top left. And I know that I'm only working with x values that are greater than or equal to 5. So what I did is I came up here and I hit my window button, which puts me into a menu, and it says my x minimum is at -10. Well, I'm not interested in that. I'm going to set it to 0 just for the moment. This thing also automatically changed my minimum y value to -150 and my y maximum to 3050. So all I've done is change my x min to a 0, and I'm going to hit graph again and see how that changes my graph. And what I've ended up with, it's even hard for me to see, is like almost a flat line. It's got a little bit of a curve to it, and it looks like it's sitting on the y-axis. Again, I apologize, this is tough to see. One of these days I'm going to get my act together, and I'll get like an emulator, and I'll be able to put this on the screen. It'll look better. But if you've got one of these calculators, I want you to know how to sort of navigate and get a decent graph of this thing. So now that I see that my curve is pretty much sitting on the x-axis, I'm going to hit the window button again, and I'm going to change my y maximum, and this is a guess, okay? I haven't actually done this yet. I'm going to change it to 50. Let's change it to 150. Since the y minimum was -150, now my y maximum is 150, my x max is 10, and I'm going to hit graph again. Let's see what we get. Oh, I'm actually seeing some kind of a curve. Oh, yeah, okay. So it came down, and then it flattened out a little, and then it dove down a bit farther into the 4th quadrant. And what I noticed from the first derivative that we looked at, where we set it equal to 0, is that our first derivative was equal to 0 when when x equaled 4 and when x equaled 5. So even though this graph looks like it kind of plateaus in the middle there, I know that what's really happening is there's actually, the graph is coming down, and then it's curving up a little bit, and then it's going back down again. So we're seeing a relative minimum and a relative maximum in there. The other thing that I'm seeing now is I'm going to go back into my window, and I'm going to change my x minimum to 5, because this function, this example problem tells us that we're supposed to be working with x values that are greater than or equal to 5. So I've gone into my window mode again, which looks like a menu, and I've changed my x min to be +5. And I'm going to change my x max to be 15, and I'll hit graph one more time. And all I'm seeing, let's go into window one more time and come down to your y maximum value, and let's make it 20. And let's change the, let's go with that. This thing's starting to look like, there it's in focus. It's really starting to look like an upside down parabola. It's all in a mirror image when I'm looking at the camera like this. So if you can see that at all, it's like an upside down parabola. So really, it's looking to me like I would need to zoom in on the top left part of that graph, right around where my p-value of 5 is. And I'd be willing to guess that that's going to end up being our maximum. The p-value of 4 is nice to know, except as you're seeing right at the beginning of this problem after our profit function, we're only working with x values that are greater than or equal to 5. If we take and we apply what we were just talking about before the previous example problem, which was the critical point theorem, it says suppose a function is continuous, which ours appears to be, on an interval I. Now we do have an interval, it's open-ended. It starts at +5 and then it goes on forever. They didn't put a cap on it. On an interval I, that f has exactly one critical number in the interval. The critical number of x equals 4 in our problem is not on the available interval. Our interval starts at positive 5 and includes positive 5. And it appears that on the interval going from x equals 5 to the right, larger x values, more production, there isn't another critical number on that interval. X equals 5 is our only critical number. And so I know that that is either going to be a maximum or a minimum. You could use the second derivative test to confirm whether it's a maximum or a minimum. You could use the first derivative and check to see if it's changing from increasing to decreasing or decreasing to increasing in order to confirm whether it's a maximum or a minimum. I would say that using the second derivative test would be a good way to go. And you can do that. You should do that. You should take the second derivative and plug in your x value of positive 5 and see whether it's concave up or concave down. In fact, let's just do it. But then I want to look at I want to talk about the graph again. So p double prime is equal to negative 6x plus 27. That should be p double prime of x. And then let's check p double prime of 5. That's equal to negative 6 times 5 is negative 30, plus 27 equals negative 3, which is less than 0. Therefore, concave down. Therefore, it's a max. It's a maximum of 12.5 when, that says when x equals 5. Let's make sure we're answering the question correctly. Find the number of hundreds of thousands of tires that must be sold to maximize the profit. That's an x value, and our x value is 5. When x equals 5, how many tires are we selling? 12.5 hundred thousand. So take 12.5, multiply it by 100,000, and if they wanted to know how many tires were being sold in order to maximize the profit, you would have your number of tires. When I was saying let's go and look at the graph one more time, we started out talking about it with a third degree polynomial that has a negative leading coefficient. Your end behavior is going to rise to the left and fall to the right. And with those other terms in there, other than just the cubic term, we had a squared term and an x to the first term and a constant term. The constant term just shifts us up and down, but those other two terms give us some character to the middle of our graph, so to speak. And we knew, or we discovered, that there was a critical value of 4 and a critical value of 5. Now remember, those are x values. Except we're only looking at our graph where x was greater than or equal to 5. And so I know that to the right of this point, where x equals 5, my graph is on its way down. It already hit its last little relative maximum. So that's how I was able to use things that we've talked about previously, and even from college algebra, we talk about end behavior based on the leading coefficient and the degree of the polynomial. I was able to use some of that old information that I had, combine it with having taken the first derivative and setting it equal to 0 in order to find our critical values, to determine, without really even doing the second derivative test, I was pretty confident that we were going to have a maximum where x equaled 5. All right, that is it for this section, my friends. I know that I rambled a little bit, but I like to try to be as thorough as possible. You know that these videos are not summary videos. These are comprehensive. I'm walking through, I'm talking about all the different perspectives and ways that you could look at these problems so that hopefully you can take something out of these and make them valuable for you. With that being said, I've got some more value to bring to you, so I will see you in the next section. Thanks so much.